In this video, I'll be using Gauss's law to find the electric field at an arbitrary distance from an infinite plane of charge. In the drawing on the left, I've decided that the infinite plane of charge is just the xy plane. And on the right, I've written Gauss's law, which says that the integral over a closed surface of the electric field vector dotted with the area vector is equal to 1 over epsilon naught times the enclosed charge of the surface. So, in this case, we'll draw a Gaussian surface that is a cube. And I hope you will believe my bad drawing that the cube is sort of centered at the xy plane, so that half of it is above it and half of it is below it. And we'll say that each face of the cube has an area of A. First, we can observe that the electric field, by symmetry, everywhere has to be pointing away from the plane of charge, because there's nowhere else for it to go. So how does that relate to the area vectors of the cube that I've drawn? Well, the area vector of a closed surface always points outward. So on the top face, it'll be pointing up. On the bottom face, it'll be pointing down. And on each of the sides, it'll be pointing out in a horizontal direction. So what we know about the dot product tells us that if two vectors are perpendicular, their dot product is 0. So we have already established that there will be no electric flux through the sides of the cube. There will be through the top and bottom of the cube. Those vectors are parallel to the electric field. So we notice that we can get rid of the dot product there. And then because the top and the bottom of the cube are at the same distance from the plane of charge, we know that by symmetry, the magnitude of the electric field must be the same everywhere on both surfaces. So we can pull that out of the integral. And that's actually no longer a closed surface. It's just going to be the top and bottom. And since we decided the area of each side of the cube is A, the area of the top and the bottom will be 2A. So the left-hand side of Gauss's law says that the electric field times 2A is equal to 1 over epsilon naught times the charge enclosed. Now, what is the charge enclosed? I know this is hard to see, but it will be the square that is the middle of the cube, right? So that's parallel to the top and the bottom face, and it also has an area of A. So this infinite plane of charge has a uniform charge density, which we will call sigma, so that the charge of this square here is just going to be sigma times its area, which is A. So we have that E times 2A equals sigma A over epsilon naught. The A's cancel. And we have that the electric field equals sigma over 2 epsilon naught.